Welcome to Molarity. So we often find substances dissolved in other substances. When two or more substances are mixed together in such a way that the particles, so these are molecules, atoms, ions, or the formula units, so that these particles are uniformly distributed, the result is a homogeneous mixture. And another name for a homogeneous mixture is a solution. And note that a solution can be a solid dissolved in a liquid. For example, sweet tea is sugar dissolved in water. Now we're not including the lemon or the ice cubes here, so we're only looking at this part of the cup of sweet tea. A solution can be a liquid dissolved in a liquid, like alcohol in water, in alcoholic beverages. A solution can be a gas dissolved in a liquid, like the oxygen in lakes and rivers that fish breathe. A solution could be a solid dissolved in another solid, like bronze. So bronze is tin that's dissolved in copper, and we see some various bronze tools here. A solution can also be a liquid dissolved in a solid. For example, the silver-mercury amalgam used in dentistry. So this is mercury in silver that is used for plugging holes in teeth. A solution could also be a gas dissolved in a solid. For example, hydrogen gas dissolves fairly well in palladium, and it's used then in hydrogen storage devices like in hydrogen-powered cars. A solution can also be a gas dissolved in another gas. For example, air is mostly nitrogen with oxygen dissolved in it. So air is roughly 78% nitrogen, 21% oxygen, and then 1% other stuff. But in chemistry, when we're discussing solutions, we usually mean a solid dissolved in a liquid. And from now on, we're going to restrict our discussion to such solutions of a solid dissolved in a liquid. But you should bear in mind that we can have other types of solutions. So the major component of the mixture, this is the one that we have more of, this is the liquid, is called the solvent. And the minor component of the mixture, the one that we have less of, this is the solid, is called the solute. The solute is then dissolved in the solvent. When a solute dissolves to a significant extent in a solvent, then we say that that solute is soluble in that solvent. If a substance does not dissolve in a solvent, then we say that that substance is insoluble in that solvent. If a substance dissolves just a little bit into a solvent, then we say that that solute is slightly soluble in that solvent. Now in chemistry, often, but not always, the solvent is water. And such solutions are called aqueous solutions, from the Latin aqua. And if a problem doesn't specify what the solvent is, then it's safe for you to assume that the solvent is water. So we have specialized glassware like burettes, shown here, pipettes, and volumetric flasks that are calibrated to accurately measure volumes of solutions. And if we know the concentration of our solution, then the volume can easily be converted into a number of moles of our solute. So solutions are often described using volume and concentration. The molar concentration, or the molarity, of a solution is defined as the moles of solute per liter of solution. So molarity is symbolized with a capital M, so we can say capital M molarity is equal to moles of solute per liter of solution, or moles of solute divided by liters of solution. So if the concentration is given or asked for, but the units are not specified, then you can safely assume that the units are molarity or molar. So to make a solution whose concentration is known, first we start out by weighing a substance, and this allows us to calculate the moles of that substance involved. And then we just need to find the volume of solution. We then take that substance and place it in a volumetric flask, and some distilled water is added to that flask to dissolve our solute. We may swirl it around. And then distilled water is very carefully added until the total volume of solution reaches the mark on our volumetric flask. And now we know the volume of the total solution. We don't know the volume of solvent that was added, but we know the total volume of solution, and then we can calculate the concentration of the solution in molarity because we know the number of moles of solute that we put in, and now we know the volume of solution, so we know moles of solute, we know liters of solution, so we can calculate the molarity. And again, note that the amount of water that we added to the flask was never measured. The total volume of solution, so this is the water plus our solute, is what is measured by that volumetric flask. So remember that molarity is symbolized with a capital M, and it's moles of solute divided by liters of solution. And that means that we can write concentration as a molarity using capital M, or as moles per liter, or as moles times liters to the -1. For example, 2.0 moles of hydrochloric acid are dissolved in enough water to make 1.0 liter of solution. Has a concentration of, we take moles per liter, so moles divided by liters, we have 2.0 moles of our solute hydrochloric acid. We divide by the total volume of solution, 1.0 liter of solution, and that gives us 2.0 molar, or 2.0 M, and that equals 2.0 moles of hydrochloric acid per liter, or 2.0 moles of hydrochloric acid times liters to the -1 per liter. And now, whenever we have a solution in the lab, we have to label that container with both the substance and the concentration. For example, 2.0 molar HCl. And we read that as 2.0 molar hydrochloric acid. Now we use square brackets around a chemical formula as a shorthand to mean the molar concentration of a solution of, and then whatever the substance that's contained within those brackets is. For example, our solution of hydrochloric acid has a concentration that we can abbreviate this way. We put HCl inside those square brackets, and now we know the concentration of HCl is equal to moles of HCl, 2.0 moles, divided by liters of solution, 1.0 liter, and that gives us 2.0 molar HCl. Now, molar concentration is a ratio unit because it is moles of solute per liter of solution. Now, we can solve molarity calculations using the molarity prompt, which says, in conversions, treat concentration, or a capital M, or molar, or molarity, or moles times liters to -1, or the square brackets around our chemical formula, as moles per 1 liter of solution in the wanted and the data. That is, each of these various representations is all equivalent, they all mean the same thing, and that all means a ratio unit. But do not write molarity as just that capital M in the wanted or the data. Ratio units should be written as a fraction in the wanted and in the data. Instead, we should write the molarity in the wanted or data as moles divided by liters. For example, what is the concentration of sodium chloride if 2.00 grams of sodium chloride is dissolved in 250 milliliters of solution? Well, what we want is the molarity of sodium chloride, but we don't want to write question mark and then a capital M and then sodium chloride. What we want to write instead is moles per liter, so moles of sodium chloride per liter of sodium chloride solution. And if the data in a problem includes a concentration, then we want to write that concentration as an equality, not as the concentration per se. For example, how many moles are contained in 100 milliliters of 0.20 molar sodium hydroxide? Well, we want moles of sodium hydroxide. The data that we have is the 100 milliliter volume of sodium hydroxide solution that we have, but we also know that 0.20 moles of sodium hydroxide is equal to 1 liter of sodium hydroxide. Now, this is the way that we are writing this concentration. Note that we're not writing it down there as 0.20 molar, we're writing it down there as 0.20 moles of sodium chloride, moles of sodium hydroxide are contained in 1 liter of solution. So we're just assuming that we have a volume of 1 liter, and then the number of moles that are contained in that are whatever value we have here, whatever number we've got there on our concentration. That's how many moles of our solute we have dissolved in that 1 liter of solution. So let's look at another example. If 2.98 grams of potassium chloride is dissolved to make 250 milliliters of solution, what is the potassium chloride concentration? First, let's write the wanted and the data sections. So the wanted is the concentration of potassium chloride, so moles of potassium chloride per liter of potassium chloride solution. In the data, we've got 2.98 grams of potassium chloride is equal to 250 milliliters of potassium chloride solution, because we know that we put in 2.98 grams of potassium chloride into our 250 milliliters of solution. And we also know that 1 mole of potassium chloride is 74.6 grams of potassium chloride from the molar mass. And remember that now we want a ratio unit. We want moles of potassium chloride per liter of solution. And that means that we need to start with a ratio unit. So in our solve, we'll start. Here we'll write our wanted unit of moles potassium chloride per liter of solution. We want to start with a ratio unit. Well, we want liters of solution on the bottom, so that's a volume of solution. Let's put a volume of solution on the bottom. The volume that we have is 250 milliliters. We know that that is equal to 2.98 grams of potassium chloride, so 2.98 grams of potassium chloride goes on top. And now we want to get rid of milliliters. So milliliters are in the bottom. We need to put them in the top in our conversion factor. And now our milliliters of solution cancels. And now we have the denominator of liters. And liters of solution is what we wanted in our wanted unit, so we're going to leave that there. But we want moles on the top, not grams of potassium chloride. So we need to get from grams of potassium chloride to moles of potassium chloride. So we put grams in the denominator. That then cancels with the grams we have over here. And that leaves us with moles of potassium chloride on the top and liters of solution on the bottom. And when we work out the numbers, it works out to be 0.160 moles of potassium chloride per liter of solution. So our concentration is 0.160 molar. So we can also use the molarity equality in problems that solve for single units. If you want a single unit, then you need to start with a single unit as the given. If you want a ratio unit, then you need to start with a ratio unit as the given. For example, how many grams of sodium hydroxide are needed to make 150 milliliters of 0.300 molar sodium hydroxide? So we want mass of sodium hydroxide, we want grams of sodium hydroxide. The data we have is that we have 150 milliliters of sodium hydroxide solution. We know the concentration is 0.30 molar sodium hydroxide, but we don't want to write it that way in the data. We want to write it instead as 0.300 moles of sodium hydroxide equals 1 liter of solution. We also know the molar mass. 1 mole of sodium hydroxide is 40 grams of sodium hydroxide. And now we want a single unit, grams of sodium hydroxide, so we need to start with a single unit. The only single unit we have is this value, so that's our given. So we write that down there. We have 150 milliliters of sodium hydroxide solution. We need to get rid of milliliters and get to liters. And now we can use our concentration. We have this equality here that we got from our concentration. We have 1 liter of sodium hydroxide that we want to get rid of. So that will get rid of our liters of sodium hydroxide solution. We then multiply by 0.300 moles of sodium hydroxide. But we don't want moles of sodium hydroxide. We want grams of sodium hydroxide. So now we know how many moles of sodium hydroxide we have. We can multiply by the molar mass. We can get rid of moles of sodium hydroxide. That gives us grams of sodium hydroxide, and that works out to be 1.80 grams of sodium hydroxide are going to be necessary. So in the previous problem on the last slide, the ratios that aren't always true were given a complete label. That is a number, a unit, and the substance. Ratios that are always true, such as 1,000 milliliters equals 1 liter, were not given complete labels. Now let's go back and look. So you can see here that we've got some ratios like grams of sodium hydroxide equals moles of sodium hydroxide. We don't want to write 1 mole equals 40 grams. And we don't want to write 0.3 moles equals 1 liter. But down here, where we have 1,000 milliliters equals 1 liter, that we don't need to have a substance formula attached. We don't need a complete label on that because that's true for any substance. 1 liter of some substance is equal to 1,000 milliliters of that substance. So we don't need to have the complete labels here. We do need to have the complete labels on all the others which aren't necessarily true for other substances. So these complete labels are important because we need to be certain that our units and the labels are canceling. So if all of one type of quantity are measuring the same substance, then you may write the complete label the first time it would be written, and then omit that label for the remainder of the times that that label would be written. You don't have to do this, and personally I prefer to leave those complete labels on all the time to make sure that I'm not confusing myself, but you can omit them if you wish. For example, in our previous problem, all of the volumes involved are of sodium hydroxide solution, and thus we can write that sodium hydroxide solution once and omit it on the remainder of the volumes. So we've got 150 milliliters of sodium hydroxide solution, and that means that now all of the remainder volumes are measuring that sodium hydroxide solution. So we have 0.300 moles of sodium hydroxide equals 1 liter, and it's assumed then that that means 1 liter of sodium hydroxide solution. If you have something involved that isn't that sodium hydroxide solution, if you have some other volume being measured, then you can't do this, and you have to keep labels on everywhere. But note that now we've got 150 milliliters, we convert to liters, convert liters to moles of sodium hydroxide, and moles of sodium hydroxide to grams of sodium hydroxide. And so it shortens our calculation a bit. But again, if at any point in the problem we have more than one substance measured with that same quantity, for example, volume of sodium hydroxide and volume of hydrochloric acid, then we have to write the complete labels on all of those quantities. So the more complex a problem is, the more helpful these complete labels will be for us. And if you're having trouble solving a problem, I highly recommend going back and adding in complete labels, and that may help you identify where you're going wrong. So make the flashcards listed on page 206 in the textbook, and run these flashcards until they're all in your got it stack. And that was molarity.